Revolutionizing microchips. Quantum machine learning breakthrough. In a groundbreaking development, scientists have harnessed the power of quantum machine learning to create semiconductors for the very first time. A breakthrough that could revolutionize the manufacturing of microchips. Microchips are the driving force behind nearly every modern gadget we use today, from smartphones and laptops to even our refrigerators. However, the intricate process of producing these chips is anything but simple. Fortunately, researchers have discovered a method to leverage quantum computing to streamline this complex task. A team of scientists based in Australia has pioneered a novel quantum machine learning technique that merges the principles of artificial intelligence, AI, with quantum computing. This innovative approach has the potential to transform the way microchips are fabricated. Their findings were detailed in a recent study published on June 23rd in the journal Advanced Science. In this study, the researchers showcased for the first time how quantum machine learning algorithms can significantly enhance the challenging task of modeling the electrical resistance within a chip, a crucial factor that influences its overall efficiency. Quantum machine learning represents a hybrid methodology that integrates classical data with quantum computing techniques. In traditional computing, information is stored in bits, which can either be a 0 or a 1. In contrast, quantum computers utilize qubits, which can exist in multiple states at once due to phenomena such as superposition and entanglement. This means that two qubits can simultaneously represent the states 0, 0, 0, 1, 1, 0, and 1, 1. This unique capability allows quantum computing systems to process intricate mathematical relationships at a speed far surpassing that of classical systems. The ability to perform parallel processing increases exponentially with the addition of more qubits to the system. In the realm of quantum machine learning, classical data is encoded into quantum states, enabling quantum computers to identify patterns that might elude classical systems. Subsequently, a classical system interprets these results or applies them in practical scenarios. Inside the chip-making process, the fabrication of semiconductors is a highly intricate, multi-step procedure that demands meticulous precision. Each phase of this process must be executed with utmost accuracy, as even the slightest misalignment can lead to chip failure. The initial step involves layering and sculpting hundreds of microscopic layers onto a silicon wafer, which serves as the foundational element of the chip. The process begins with deposition, where thin films of material are applied to the wafer. Following this, a photoresist coating is added, which is a light-sensitive material that facilitates precise patterning. This is the technique used to create the tiny, complex shapes that define a chip's circuitry. Lithography then employs light to transfer these patterns onto the wafer's surface, while etching removes specific areas of material to carve out the circuit structures. Ion implantation is used to modify the electrical properties of each layer by embedding charged particles. Finally, the chip is packaged, encasing it and connecting it for integration into various devices. This is where the principles of quantum computing come into play. The researchers concentrated on modeling ohmic contact resistance, a particularly challenging aspect of chip manufacturing. This resistance measures how easily electricity flows between the metal and semiconductor layers of a chip. A lower resistance translates to faster and more energy-efficient performance. This modeling step occurs after the materials have been layered and patterned onto the wafer, and it is vital in determining the functionality of the finished chip. However, accurately modeling this resistance has posed significant challenges. Traditionally, engineers have relied on classical machine learning algorithms to identify patterns in data and make predictions. While these algorithms perform well with large, clean datasets, semiconductor experiments often yield small, noisy datasets with nonlinear patterns, where classical machine learning can struggle. To overcome this limitation, the researchers turned to quantum machine learning, a new kind of algorithm. The research team utilized data from 159 experimental samples of gallium nitride high electron mobility transistors, GaN-HEMTs, which are semiconductors recognized for their speed and efficiency, commonly found in electronics and 5G devices. They first pinpointed which fabrication variables most significantly impacted ohmic contact resistance, refining the dataset to include only the most relevant inputs. They then developed a new machine learning architecture known as the Quantum Kernel-Aligned Regressor, QKAR. QKAR transforms classical data into quantum states, allowing the quantum system to uncover complex relationships within the data. A classical algorithm subsequently learns from these insights, creating a predictive model to guide the chip fabrication process. The model was tested on 5 new samples that were not part of the training data. The results were impressive. The new model was evaluated against 7 leading classical models, including deep learning and gradient boosting methods, and it outperformed all of them. QKAR achieved a significantly better result than traditional models, with a resistance measurement of 0.338 ohm per millimeter, although specific figures were not disclosed in the study. Crucially, this model was designed to be compatible with real-world hardware, meaning it could be implemented on quantum machines as they become more reliable. The researchers concluded that their findings highlight the potential of quantum machine learning, QML, to effectively tackle high-dimensional, small-sample regression tasks in the semiconductor field. They expressed optimism that this method could soon be applied to actual chip production, especially as quantum hardware continues to advance.